Hello everyone, my name is Kayla Rodriguez and this is my homework assignment number 3, covering chapters 2 from our principles of strength and conditioning with Dr. Dorgo. In this presentation, I will discuss the 3 class levers, the first, second, and third, explain how mechanical advantage changes among these levers and how they relate to our human body, and then describe changing exertion during joint movement, and finally calculate power and movement velocity for 2 lifting examples, the snatch and the deadlift. First things first, what is a lever? A lever is a rigid structure that rotates around a fixed point called an axis or fulcrum. Levers allow muscles to produce movement by applying force to bones, and every lever contains 4 basic components. There's a rigid bar, which is usually our bone, the axis or fulcrum, which is the joint, and the applied force, also called the effort, which is produced by skeletal muscle, and the resistance, which may be body weight or an external load. So just to give you a little bit of a visual, right here would be the axis, rigid bar, and then the applied force would be the skeletal muscle, and the resistance would be maybe body weight or an external load, just right there. That is our levers. So in a first class lever, the axis is positioned between the effort and the resistance. Common world example, or a common example we see in biomechanics, was the seesaw. And then in the human body, an example occurs during the neck extension at the atlanto-occipital joint. The fulcrum in this example would be the atlanto-occipital joint. The effort comes from the posterior neck muscles, and the resistance is the weight of the head. And depending on where the effort and resistance are located, first class levers may either increase force production or increase movement speed. In a second class lever, the resistance is located between the axis and the effort. For this lever, a wheelbarrow is commonly used in biomechanics as an example, and in the human body, this occurs during let's say a heel raise, while standing on the toes. Very specific here, that would be the metatarsophalangeal joints acting on as the axis, and the body weight serves as the resistance, and the gastrocnemius and soleus apply the effort through the Achilles tendon. Second class levers have a mechanical advantage greater than 1, meaning they require less muscular force to move a relatively larger resistance. Moving on, we have our third class levers. This is the most common lever found in the human body. In the arrangement, the effort is located between the axis and the resistance. So let's say during an elbow flexion exercise, such as a bicep curl, the elbow joint is the axis, the biceps brachii applies the effort, and the dumbbell would be the resistance. And then, although third class levers have a mechanical disadvantage, they allow greater movement speed, larger range of motions, and higher endpoint velocity, making them very ideal for athletic performance. Going back, mechanical advantage describes how efficiently a lever converts muscular force into movement. It is calculated as mechanical advantage equals the motive force, or the effort arm, divided by resistance arm, or resistance force. If the value is greater than 1 in this equation, the lever favors force production, and if the value is less than 1, the lever favors speed and range of motion. Second class levers, as I said before, generally have a greater mechanical advantage, or have the greatest mechanical advantage. And then third class levers generally have the lowest mechanical advantage. And again, even though third class levers require much greater muscular force, they allow us to throw, to sprint, to jump, and perform very fast and explosive athletic movements. One important concept introduced in chapter 2 is that muscular effort is not constant throughout a movement. Even if the external weight does not change, the amount of muscular force required changes because the moment arm changes, and a moment arm is the perpendicular distance between the line of force and the axis of rotation. So as joint changes angle, the distance also changes. So during an elbow curl or a bicep curl, the resistance moment arm increases as the forearm approaches horizontal meaning that the external torque becomes greatest when the forearm is about parallel to the floor. And as a result, because of that, the biceps must generate the greatest muscular force at this position. And as the elbow continues moving beyond 90 degrees, the resistant moment arm becomes shorter. Even though the dumbbell weighs the same, less muscular force is required because the external torque decreases, therefore muscle effort changes continuously through the range of motion. So this concept of the moment arm explains why some portions of an exercise feel way more difficult than others. And it also explains actually why coaches may use resistance band, chains, or specialized machines to better match the body's changing strength and curve throughout an exercise. So for our physics calculations, very important equations to know is force equals mass times acceleration. We have work equals force times displacement, power equals work divided by time. For our first calculation, we'll be doing a deadlift that was 150 kilograms over 30 centimeters off the ground, and then it took 2.5 seconds. And we're finding power. So the first thing you need to do is find the force. So that would be the first equation. Force equals mass times acceleration. So 150 kilograms is your mass, and acceleration is negative 9.81. That equals to 1,471.5 newtons. And from there you can find work, and that's where you would bring in displacement. So that Newton, that force number times the 30 centimeters, which was converted to meters, so 0.3, and that gives us 441.45 joules. And then from there you can find power, and you would just need to bring in the how long it took, so 2.5. So it's work divided by time, and that gives us a power of 176.58 watts. And now we will be finding the power for a snatch. So our information that was given was 75 kilograms to over 2 meters, and then over 0.5 seconds of time. Finding force first. Force equals mass times acceleration. So 75 kilograms times negative 9.81 meters per second squared, and that gives us 735.75 newtons. From there you can find work. You would just need to multiply times 2 meters. This one doesn't need to be converted from centimeters to meters because it's already in meters. And then we get 1,471.5 joules. From there you can find power. You would just need to divide by 0.5 seconds of how long it took. And that gives us a power of 2,943 watts in that snatch. From these two, we can obviously tell that the snatch has more power. And then another thing we have to solve for is our average momentum velocity. This, for the deadlift, you would just need to find meters per second, that's velocity. So it's a 0.30 meters of movement divided by 2.5 seconds, and that gives us 0.12 meters per second for the average movement velocity. And then for the snatch, it was 2 meters divided by 0.5 seconds, and that gives us 4.0 meters per second for the average velocity. And going back to why the snatch is more powerful, very conceptual question. So even though if you couldn't tell, this uses a little less than half of the time compared to the deadlift. So why doesn't the deadlift have more power? Obviously, from the equations we can tell it depends not only on force but how the quality of work is performed. So the Olympic lifts are designed to move moderate loads at extremely high velocity, and deadlifts emphasize maximal force production, whereas the snatch emphasizes explosive power. And that's why Olympic lifts are given to college athletes, to really any athletes in high school, any professional athletes, and sprinters, football players, volleyball players, and Olympic weightlifters, because it's such a powerful movement. So in conclusion, chapter 2 demonstrates how biomechanics influence human movement. Understanding the lever systems, the mechanical advantage, changing moment arms, and the relationship among force, work, power, and velocity helps strength and conditioning professionals select appropriate work exercise appropriate sessions, exercises, and really improve the athlete's performance. Although the human body often sacrifices mechanical advantage through the use of third-class levers, this design allows greater movement speed, range of motion, and functional performance. Thank you for watching.